Chapter 6, Momentum and Collisions. So we're talking about momentum, and the question is, what is moment? Or momentum? Momentum is the inertia of a body in motion. So when you're talking about momentum, you have to think about inertia. What's inertia? Inertia, if you think back into Newton's laws, the first law refers to the tendency of an object to maintain its state of motion. Meaning, if an object is moving, it's going to keep moving. If an object is stationary, it's going to continue being stationary. Well, momentum is inertia of a body that's moving. So there's inherently a movement part of the equation here. So let's look at this. How do we calculate momentum? Momentum, signified by P, is mass times velocity. So which has more momentum? A parked semi-truck or a Hot Wheels car that's rolling? Well, the semi-truck is parked, so its velocity is 0. While it has a much greater mass, its velocity is 0. The Hot Wheels car, while having a small mass, would have some velocity and therefore would have more momentum. An example, Bob has a mass of 100 kilograms. If he's traveling at 10 meters per second, what's his momentum? 100 times 10, his momentum will be 1,000. Another example, we would simply take the mass of our truck here, 2250 kilograms, and multiply it by our velocity here of 25 meters per second. So you simply multiply those two together, and you get 56,250. And if you're keeping track, there's the homework 191. Now we're going to move forward with the notes, though. There is a video on the 191 homework already. So moving on with the notes. And we're going to talk about a very important idea in this chapter called impulse. The idea of impulse is change in momentum, delta P. So change momentum of an object. So we've learned change in momentum is often done by taking the final something minus the initial. So we can start saying that impulse is final momentum minus initial momentum, MVF minus MVI. Well, there's another idea with impulse that we're going to learn, and that is that to change momentum, you can apply a force to an object for a certain time frame. And if you do a little bit of relating equations together, you can see the blue and the red are equal to one another. So you can write it like this: force times time equals MVF minus MVI. So what does this mean? Force times time equals change in momentum. So you got an egg thrown at you. You could catch it straight arm. Just stick your arm straight out, elbow locked, and catch the egg that way. Or you can make it like a basket catch where you cradle it as you catch it. With these two methods of catching, which ones that take a longer time to stop the egg? Well, the basket catch takes a longer time. If the time is longer, you'd have more time. In both ways of catching it, you're stopping the egg. Initial velocity is still going to go to the same final velocity of 0. So the change in momentum on this side of the equation will be the same regardless of your catching method. But if you catch it with a straight arm, you have a small time. If you catch it with a basket catch, it's a big time. The larger the time, when this is equal, the smaller the force. And that's what you want when you're catching an egg. You want a small force. So which one's safer for the egg? The basket catch is safer for the egg because the time of catching is greater. An example of hockey. A skater is skating full speed down the ice. Another player slams into him head on, stopping him in his tracks. Would this be more or less impulse than if he applied his brakes and skated to a stop? Well, in both examples in the question, we are skating to a stop, meaning the player is stopping. The change in momentum is the same. All we're talking about is the difference in the way the momentum is changed. The impulse would be the same. The impact will be much greater when this stopping is very quick versus if you just gradually skate to a stop. The impact is much less. So, again, is stopping something abruptly more or less gentle? Abrupt stops are less gentle, meaning there's a greater force because there's a smaller time. Which one's greater impulse? The impulse would be the same. Impulse is delta P. Baseball. A nice example here. Force times time. So you've got your time here. You can put the time in. It's a very small time. We've got mass of the ball. Where's that? There it is. You can put the mass in for the ball, and you can put in your velocities. Now, one thing I want you to notice: initial velocity is 40 there. Final velocity is 49. Now, one thing about this: the baseball is coming toward you at 40 and away from you at 49. This is an issue. We have to make sure that when we do impulse problems, we are making sure the velocities have an appropriate negative sign if you have opposite directions happening. Because we're not just changing the speed of the ball by by 9, we're changing the speed of the ball by 89. It's a huge change in velocity. So you need to make sure that you put a negative on one of these two velocities as you do this. I would put it here. And you'll be able to calculate that on your own and find the force applied to the ball. It would be a very big force because of this. We're not going to do that or that. Hey, turn. So, that's going to be enough for that video.